Welcome back to the course of micro engineering and very good morning to all. So today in the 23rd lecture we are going to proceed further for the interpretation of the waveguide analysis. Last time we have gone through the rigorous derivation of transverse electric mode and transverse magnetic mode for the two different types of waveguides, that is for rectangular waveguide and for circular waveguide. So we will proceed further and we will investigate these field equation and some of the important feature and inferences we are going to draw based on our observation. So I hope last time you understood how to derive the mode equation wherein the transverse electromagnetic components are expressed in terms of longitudinal field component for the two different types of waveguide. In today's lecture, we are going to see further the different parameters, equations, the definition of cutoff frequency, then the wave number, phase shift constant, and all other important parameters related with the calculation of the rectangular and circular waveguide we are going to illustrate. We will also see the resonator concept, and we will observe that how the resonator circuit or resonator devices are going to get constructed using the waveguide device. And then afterwards we will start with passive waveguide based junction devices. So for that purpose I will take the help of my book. Now we already derived the equation for field component, that is the modal analysis we already performed for rectangular waveguide and for circular waveguide in transverse magnetic mode and in transverse electric mode. Okay, so the same geometry is shown over here, the rectangular waveguide, and the equation for the transverse magnetic mode are given over here. Okay, so these are the set of equations. So we already know that in transverse magnetic mode the Ez component, that is the electric field component along the direction of propagation, is a non-zero. Okay, and that is given as a Ez, while Hz component is 0. And by applying that theory, the other remaining four components Ex, Ey and Hx, Hy can be calculated. So we have in front of us all the equation for the transverse field component and longitudinal field component for the transverse magnetic mode of the rectangular waveguide. Now here are some important observations. Okay, so already we have derived these equations, and there we define what is the meaning of small m and small m in these equations, right? So here the small m and small n, they indicate integers and they define the order of the particular mode. Okay, and the mode is designated as a tm to the suffix mn mode. Okay, so if I here denote, right, so the particular mode of transverse magnetic condition in rectangular waveguide is denoted by te to the suffix m and n, where m and n, they stand for the integer and they represent a specific type of a mode. So today we are going to see the details of these modes and what do you mean by the significance of these modes, right? So if we observe these equation carefully, equation 2.100 to 2.104, the important observations are as follows. The field is going to exist in a discrete pattern. Okay, and the pattern in which the field is going to exist, we used to call it as a modes. Okay, so simple definition of the mode is the specific pattern in which the field exists inside a given rectangular waveguide. That particular pattern of the field, we used to call it as a mode. Okay, so here if you observe all the field components, okay, all the field components, if you see here from the Ez, Ex, Ey, Hx and Hy. Anyway, in the case of a transverse magnetic mode, the Hz component is already 0, right? So if you observe all these equations on the right hand side, we will find that there is a sine and cosine terms. Okay, so what these indicate? These indicate that the fields are going to vary sinusoidally. Okay, so this is an important observation. So for a rectangular waveguide in TM mode, the fields are going to vary sinusoidally. So this is the first observation. Okay, next is a very important observation. The subscript over here, which we represent with the letter M and N, we already called them as an integer. Okay, what they represent? They are going to take discrete values of numbers. Okay, they are going to take integer numbers, for example 0, 1, 2 and 3 and so on. Okay, so what these are going to represent then? They are going to represent the number of half cycle sinusoidal variation of the field along the x-axis and along the y-axis. So for example, if I say m is equal to 2, so that means that there are two half cycle variation of the field along the x-axis of the rectangular waveguide. And similarly, if I take the example n is equal to 3, that indicates that there are three half cycle sinusoidal variation of the field along the y direction. Okay, so next observation is very important. All the transverse component. Now here, if you notice, we have in total 5 components: Ez, Ex, Ey, Hx, Hy. Okay, and anyway, Hz is going to be 0 for the TM mode. So we have total 5 components. Out of these 5 components, how many transverse components are there? The transverse component are only 4. Okay, and these are Ex, Ey and Hx and Hy. So these are the 4 transverse field components. So the Ex, Ey, Hx and Hy, they becomes 0 if either small m or small n is going to be 0. So you look into details of this equation. Say in equation 2.101 to 2.104, if we substitute either small m or small n is equal to 0, what will happen to these equations then? Say if I substitute either m or n is equal to 0 in this equation on the right hand side, all the field components Ex, Ey, Hx and Hy, they are going to become 0. Please remember. Okay, so this is a very important observation. All the transverse field component, they will become 0 if either m or n is going to 0. Okay, so in other words, the indices, so what is m and small m, they have to be non-zero. Okay, so if you substitute either m is equal to 0 or n is equal to 0, all the 4 transverse components are going to become 0. Okay, so in other words, if we don't let the component to become 0, then we need to keep m and n equal to non-zero. Okay, so what it indicates then? The small m and small n values. So here I will underline small m and small n values have to be non-zero. Okay, so only for this particular condition, if the small m value and small n value are non-zero, then only in that particular case these components are going to exist. On the other hand, if m is equal to 0 or n is equal to 0, all these field components will become 0. Okay, so what is the necessary condition so that the transverse field component are going to exist? The condition is that in TM mode, the indices or the suffixes small m and small n, which are representing integer, they have to be a non-zero for the existence of TM mode. And therefore, we cannot make either m is equal to 0 or n is equal to 0. And that is what it is given in this particular sentence. So that is, we cannot make TM M0 mode or TM0N mode. Okay, so what we want is, we want the m value and n value to be other than 0. So other than 0, what is the next number? The minimum number is a 1. Therefore, the lowest possible mode in TM configuration is a TM11 mode. Because we cannot put either m is equal to 0 or n is equal to 0, then the minimum number that we can put is 1, 1, where m is equal to 1 and n is equal to 1. Okay, so the minimum possible mode in the rectangular waveguide operating in TM mode is TM11 mode. Okay, so this is a very important observation in the TM mode configuration of a rectangular waveguide. Okay, so similarly, let us study the important properties and investigation of the field equation which we get with the transverse electric mode of the rectangular waveguide. So the transverse electric mode of the rectangular waveguide, it indicates that Ez is 0 while Hz is non-zero. Okay, so the Hz is given over here with this particular equation, right? So Hz is non-zero while Ez is 0, and again we have took these field equation in the other directions. Okay, now again over here we will make certain observation. Okay, as usual, the right hand side of all these equations from 2.113 to 2.117, they indicate that the field is going to vary sinusoidally and in a cosine way, right? The M and N here also, they indicate the number of half cycle variation of the field along the x direction and along the y direction. So this definition of the integer is same in this mode also. Now here the transverse electric field, it exists in a discrete field pattern. So the pattern in which the transverse electric field exists, we used to call it the transverse electric mode. All the field components, they have sinusoidal amplitude variation along the x and y direction. That is obvious if we study on the right hand side of these equations. We all find that these equations are going to contain sinusoidal and cosine terms, right? Next, as usual, the suffixes m and n are going to indicate number of half cycle variation of the given field in the x direction as well as in the y direction, right? Now, the sinusoidal variation for the electric and magnetic field, they are shifted with respect to each other in a space by quarter cycle. Okay. Now, here the next important observation is either m or n has to be a non-zero. Okay. So, here if you observe, if I put m is equal to 0. Okay. So, if I put m is equal to 0 in this particular equation, the Hz equation is a non-zero, right? Now similarly here, if I put m is equal to 0, again the Ex component becomes non-zero. So that means if I observe over here, if I put either m or n equal to non-zero, that means m and n value either of one value is non-zero, then at least some transverse field are going to exist. Okay. So if we put both m and n is equal to 0, if we put m and n is equal to 0, what will happen then? If I put both component is equal to 0, m and n, Hz is going to be a non-zero. Okay, Hz is going to be a non-zero. It appears it cannot exist but without any electric field. Okay, so TE00 mode cannot exist, but please remember TEM0 or TE0N mode can exist. So over here. Okay. So this is unlike the situation of a TM mode. In a TM mode of a rectangular waveguide, we saw that in order to exist the transverse field component, the indices m and n have to be non-zero. But in the case of TE mode, what we understood is in order to exist some of the transverse field component, either m or n has to be a non-zero. Both should not be non-zero. Either of one should become non-zero. And in that particular case, if m is equal to 1, considering n is equal to 0, we will get TE10 mode. And reversely, if I take m is equal to 0 while n is equal to non-zero, that is 1, we will get TE01 mode, right? So we go ahead and then we will see what is the cutoff frequency in the rectangular waveguide. Okay, so here this particular equation beta is equal to square root of omega square mu epsilon minus m pi by a whole square minus n pi by b whole square. This particular equation is going to give us the phase constant of the propagating wave in the given waveguide, rectangular waveguide. And this phase constant equation is same for TE mode as well as TM mode. Okay. So in order to make the wave traveling in nature, what we know that in order to make sure that whatever the wave that is propagating through the rectangular waveguide, if it has to be in a traveling nature, then the phase constant should be a real value. Okay, so the frequency at which, the operating frequency at which the phase constant beta changes from real to imaginary, that particular frequency of the operation we call it as a cutoff frequency. So here this is a very important term, the frequency at which the phase constant of the waveguide changes from real to imaginary. Okay, so when it changes from real value to imaginary value, that means the wave traveling becomes stop. Okay, so when the phase shift constant is real value, that indicates that the wave is traveling, and when the phase shift becomes imaginary value, at that time the wave will not travel. Okay, so the operating frequency at which this particular thing happens, we call it as a cutoff frequency of the given mode. Okay, so what we do is, in this particular equation 2.119, beta is originally some real value, and when it becomes imaginary, it will passes through a zero value. So if we equate beta is equal to 0, okay, and if we rearrange the term on the right hand side, we will get the cutoff frequency radian expressed in a radian given as a omega c. Okay, so what we do is, we will put in equation 2.119 beta is equal to 0, and we will calculate the cutoff frequency. Okay, and this cutoff frequency is the radian frequency, and you can express that in a linear frequency, omega is equal to 2 pi fc, right? So you can write the cutoff frequency in terms of a linear value, fc is equal to. So here a very important uh, equation of the cutoff frequency we will get, that is fc is equal to 1 upon 2 pi under root mu epsilon square root of m pi by a whole square plus n pi by b whole square. So this is a very important equation, and this is a generalized equation for the cutoff frequency of the waveguide, and which is common for both the modes of the rectangular waveguide, that is TM mode as well as TE mode. Okay, so in the case of TM mode, what we know in the case of a TM mode is that the lowest TM mode possible is TM11. So here in this particular equation 2.121, what we do is, we replace m, small m and small n by 1, 1. Okay, and this will give me the cutoff frequency of TM11 mode. Okay, so if you substitute this value, I will get equation number 2.122. Similarly, the cutoff frequency for the lowest order mode in the case of TE mode, we can similarly write the lowest possible mode that do exist in TE mode of a rectangular waveguide are TE10 and TE01. So first of all, you substitute m is equal to 1 and n is equal to 0 in equation 1.2.1, you will get this particular equation. And similarly, if you substitute m is equal to 0 and n is equal to 1, you will get this particular equation. Okay, so now what we want is, we have calculated the cutoff frequency of a rectangular waveguide in different modes. First, we have calculated that in TM mode and then in a TE mode. Now we will see in which particular case the cutoff frequency is minimum and in which case the cutoff frequency is maximum. So here, if you compare equation 2.122 and 2.123, okay, so here the dimension of the waveguide is going to influence the cutoff frequency. Okay, so dimension A is greater than dimension B, right? Because A is going to stand for the width of the rectangular waveguide, while the height of the rectangular waveguide is indicated as a B, right? So TE10 mode, okay, so this particular mode will be a lowest value because it is divided by A. Okay, the cutoff frequency of TE01 mode will be higher than this, and the cutoff frequency of TM11 mode will be the highest of all of three. So if you compare the cutoff frequency values in all these three different modes, in which two modes are TE mode and one mode is a TM mode, so we will get this particular equation. Okay, So hence the lowest frequency at which a signal can propagate through the rectangular waveguide is TE10 mode. So from equation 2.124, we can understand that the minimum frequency with which the signal can propagate through a given rectangular waveguide is going to get operated in TE10 mode, and therefore the smallest operating mode or the cutoff mode of the rectangular waveguide is TE10 mode, right? So please remember that no energy can propagate in a rectangular waveguide at a frequency below this TE10 mode. So that means a signal, whenever it want to get propagated through the rectangular waveguide, the minimum frequency should be TE10 mode. The frequency, if it fails below TE10 mode frequency in a given particular rectangular waveguide, the signal cannot propagate, right? And hence the absolute cutoff frequency of the rectangular waveguide is specified by TE10. This is a minimum frequency. Okay, so the meaning is that whenever you want to pass a microwave signal through a given rectangular waveguide, the frequency of that microwave signal should satisfy this condition. Okay, so what it should satisfy? The frequency should be such that it is at least equal to TE10 mode frequency, which is given by this particular equation over here. Okay, so how that is going to depend then? So the frequency should be calculated by taking into account the broadest wall of the rectangular waveguide and the medium. It also depends on the medium, permittivity and permeability, right? So it is observed from the general equation of cutoff equation given in equation 1.2.1 that the order of the mode increases, the cutoff frequency also increases. Okay, so irrespective of the dimension of the waveguide, TE10 mode always has lowest cutoff frequency. So this is a very important sentence over here. TE10 mode will always has lowest cutoff frequency. So the cutoff frequency is that frequency below which the signal cannot propagate through a given rectangular waveguide. So please remember that whenever you want to make use of a waveguide to transmit a microwave signal from one position to another position, the frequency of that microwave signal should be at least equal to or greater than TE10 mode frequency of that waveguide, which is calculated with this particular equation. If your frequency of microwave fails below this particular value, that particular microwave signal will not be propagated through the given waveguide, right? So as we know the minimum frequency, we can calculate the cutoff wavelength on the similar basis, right? So the cutoff wavelength can be calculated once you know the cutoff frequency. So we know this cutoff frequency, so we can calculate the cutoff wavelength, and this is given by equation 2.125. Okay, so the cutoff wavelength is given by 2 divided by square root of m by a whole square plus n by b whole square, right? So the cutoff wavelength for the dominant mode. So the dominant mode is the minimum mode at which the signal propagation take place. Okay, and we already know that TE10 mode is the dominant mode. What is the dominant mode? The dominant mode is the mode of operation of the rectangular waveguide with minimum cutoff frequency, right? And we saw that the minimum cutoff frequency mode is TE10 mode, and that's why the dominant mode of the rectangular waveguide is TE10 mode with m is equal to 1 and n is equal to 0. Okay, so when we substitute m is equal to 1 and n is equal to 0 in this particular equation over here, say this is the cutoff wavelength equation. So substitute m is equal to 1 and n is equal to 0 in this equation, we will get the cutoff wavelength in TE10 mode operating in dominant mode, and we will get 2 times A. Okay, and hence we can calculate what must be the value of the width of the rectangular waveguide from this equation. So the width of the rectangular waveguide is then found from this equation. You can take it is cutoff wavelength in the TE10 mode divided by 2. Okay, so this equation indicates that the longest wavelength that can propagate in the given rectangular waveguide, so the longest wavelength is given by this, is equal to twice the width of the rectangular waveguide. Please remember. So this is a very important observation. In a rectangular waveguide, the maximum wavelength with which the wave can propagate is given by twice of the width dimension of the rectangular waveguide, right? So this is a very important consideration. Then afterwards, we will discuss what is a wave number and all those things. Okay, so here the wave number is denoted by k is equal to, now here I will underline that term. So a wave number is calculated by using this particular equation, omega square root of omega 0 epsilon r. Okay, and this denotes the real wave number in the absence of any particular loss. Okay, and the cutoff wave number is denoted by the letter kc. Okay, so where kc is equal to square root of k square minus beta square, where k is a real wave number. Okay, so we can find out the equations and we can summarize the different equations in the rectangular waveguide, and the summary of results in the rectangular waveguide are mentioned over here. Okay, so we know that there are two distinct separate modes supported by the rectangular waveguide, and that is TE mode and TM mode, where the mode is indicated with the letters M and N, right? So the real wave number is given with this particular equation. The cutoff wave number, okay, so it is given by the second equation. Beta is a phase shift constant and it is the square root difference of square of the real wave number with the cutoff wave number. The cutoff wavelength is given with the fourth equation, and then the guide wavelength. Okay, so the guide wavelength is going to dependent on the material with which the rectangular waveguide is constructed, and the phase velocity, the velocity with which the signal is propagating in the given waveguide, is given by this particular equation, phase velocity. Okay, and then finally the important factor is the wave impedance. So the wave impedance is expressed, it is given with this particular equation. In the case of a TE mode, it is the product of real wave number multiplied by eta divided by b. Okay, and in the case of TM mode, it is eta multiplied by b divided by k. Okay, and here in this particular diagram, sum of the cutoff frequency versus attenuation for the few modes of the rectangular waveguides are shown. Okay, now here if you recall over here, the TE10 mode in the initial, so the horizontal axis is the frequency axis, right? Vertical axis is the attenuation axis. Now for meantime, you just forget about the vertical y-axis and concentrate on x-axis over here. Now at the x-axis, for the given dimension, the TE10 mode is the minimum operating mode, right? So TE10 mode is the minimum operating mode of the rectangular waveguide, and which is already known as a dominant operating mode, right? So here is a discussion of all the field components of TE mode and TM mode of a rectangular waveguide, and we saw the definition of the cutoff wave number, the cutoff frequency, the cutoff wavelength, then the propagation constant, then the phase shift constant, impedance, and all those things. Okay, so let us come to the similar technique and investigation of field component equation for the circular waveguide. We already derived the field equation for the circular waveguide separately in TE mode as well as in TM mode in our previous lectures. Okay, so let us investigate. So that time, if you recall, we took the use of the this one Bessel function over there. Okay, so that Bessel function, we have made use of the equation in the case of evaluating the Bessel functions. So that time we discussed the Bessel function. So these Bessel function, these are complex functions. Okay, so the some of the JV function of Bessel functions are shown over here. Okay, so Bessel functions are denoted as a very complex functions, and they do have sinusoidal variation. Okay, so here if you go to the equations, the transverse electric mode of a circular waveguide in which we consider Ez is equal to 0 while Hz is not equal to 0, and we can consider the field inside and field outside separately, provided if the dielectric constant of the inside and outside of the circular waveguide is separate, right? So these equations we already derived, right? Now similarly over here we are interested to see how to calculate the cutoff frequency for the circular waveguide. Okay, so come to this particular part, cutoff modes in a circular waveguide. So here the cutoff frequency for the circular waveguide, is given with this particular equation directly. Okay, now let us see to this particular equation. So omega c is a cutoff frequency expressed in a radian. So you can replace omega with a 2 pi f and you can calculate the cutoff frequency in a linear value. So how it is given? It is equal to, in the numerator we have chi 0 of m, okay, divided by a into square root of mu into product of difference between first dielectric material to second dielectric material, where epsilon 1 is the dielectric material which is placed inside of that circular waveguide, and epsilon 2 is the dielectric material which is surrounding the circular waveguide. Okay, so normally if we take air as a surrounding material, epsilon 2 will become equal to 1. Okay, and what is psi 0 m? The psi 0 m value over here, it represents the root value for the Bessel function. So this is a very important over here. So psi 0 m value represent root value for the Bessel function, and it is denoted separately for the TM mode and for the TE mode. For the TM mode, it is denoted by p to the suffix nm, and while for the TE mode, it is denoted by p dash to the suffix nm. Okay, so here let us see what are these values for TE mode and for TM mode. Okay, so these root values of the Bessel functions are given over here, and these are separately. So for TM mode, we already know for TM mode it is expressed as a PNM, okay, where n value can be from 0 to 1, okay, while m can proceed from 1 to 3, right? So these are the root values. Okay, so the depending upon the given mode of operation, you can substitute the value of these roots of the Bessel function into the cutoff wave. Okay, so the first root of the Bessel function, so over here, so the first root of the Bessel function is p n m. Okay, so p n m p01, that is a 2.4. Okay, so if you observe this particular equation over here, that is Pn1, the first root is 2.4. Okay, so this first root we will place over here, and we can calculate the cutoff frequency for the TE and TM mode. Okay, so 2.4 divided by a square root of mu into multiplied by the difference of two dielectric material. Okay, so this is a particular equation with which we can calculate the cutoff frequency for the circular waveguide, and this is a general equation 2.1.9.1. Okay, we go ahead and we will see that what are the different cutoff frequencies available for the circular waveguide. Okay, so here we will denote the TE11 mode. Please remember, TE11 mode is the minimum cutoff frequency for the circular waveguide. In the case of rectangular waveguide, we saw it was a TE10 mode. Okay, and in the case of circular waveguide, it is a TE11 mode. Okay, so all these basic equations are going to be required whenever we solve mathematical solution for designing a particular waveguide. Okay, so that part will be clear to you when we solve some of the numericals based on waveguides. We go ahead to the next part in our syllabus, which is devoted to microwave resonators. Okay, so resonators are nothing but a tunable circuit. Okay, and these tunable circuits are used in oscillators, amplifiers, filters, and frequency meters. Okay, so in microwave circuit, the role played by the resonator is very important. And what is the property of a resonator? The resonators are going to resonate at a particular specified frequency. For example, if you want to take the application of a resonator, take the example of simple LC tuned circuit. Okay, or we used to call it as a tank circuit, in which an inductor and capacitor, they are placed in a parallel, and we go on changing the value of inductor and capacitor in order to tune that particular tuner circuit. Okay, so the best example of resonator is tank circuit, which consists of parallel combination of inductor and capacitor. Okay, now the same is applicable over here. What is the important property of the resonator is the resonator will start resonating at a specific value of frequency. Okay, so this particular frequency we used to call it as a resonant frequency of that resonator. Okay, so what actually happens during this operation? The average stored electric and magnetic energies are going to become equal, and thus they tend to cancel each other, and therefore the entire circuit will become purely resistive. Okay, and hence it will start resonating. The electric energy stored in the form of a capacitor, while the magnetic energy is stored in the form of an inductor. Okay, so the resonating frequency and the quality factor of the resonator are the important parameters of the circuit. Okay, so how the quality factor is given? The quality factor is given with this particular equation. Q is equal to, in the numerator, 2 pi multiplied by energy stored divided by energy dissipated per unit cycle. Okay, so in order to calculate the quality factor of a resonator, we should know what is the energy stored and what is the energy that is dissipating per unit cycle. Okay, so once we know, we can put these values over here and we can calculate the quality factor. We already know that the quality factor for any particular resonant circuit is very high. Okay, so as the resonator is going to exhibit resonance characteristic at a particular frequency, please remember that the resonator will only start resonating at a particular frequency and not at all the different frequencies. So it is a very selective circuit, and we can say that a resonator possesses a very high frequency selectivity. Okay, so the typical values of the quality factor associated with a resonator circuit will be in the range of around 10,000, which is specified over here. Okay, so here you notice that the typical values of quality factor associated with resonator devices is very high, and that is around 10,000. Okay, so what that indicate? High quality factor value indicate that the circuit has a capability to store large amount of energy, right? So at the resonance, electric and magnetic energies are going to become equal, and hence they tend to cancel each other, and the resonator circuit will become purely resistive. Please remember. Okay, so how to construct a resonator? Okay, so resonators can be constructed using a transmission line, okay, as well as using the waveguides. Okay, so normally resonators constructed using a waveguide will provide us minimum loss, and that's why rectangular cavity based resonators are popular in application. So such a two configuration of a resonators are shown over here. So what we observe over here, the resonator is nothing but a waveguide which is terminated at the length which is indicated along the z direction. Okay, so in a rectangular waveguide, what we consider is the z direction we normally consider to be infinite in length. Okay, so when that infinite length along the z direction is truncated, when it is limited with a certain distance which is given by d over here. right? So it will become the resonator circuit then. So the two dimensions are already fixed, that is the width, which is along x, right? This is the width along x, and the height along y. Those are already fixed for the rectangular waveguide. When we fix the rectangular waveguide along the propagation direction with certain dimension, that is d, then that waveguide will get converted into a resonator circuit. Please remember that resonator circuit is a closed circuit in all direction, while the waveguide is closed only in a two direction. Okay, the same is applicable. We can construct a resonator using a circular waveguide, which is terminated and limited at the propagation direction by placing the walls. Okay, so waveguide cavity resonators are very important. So how these are formed? The cavity resonators using the waveguides are formed by shorting the two ends of the waveguide, right? So what we have done over here in the first image, we have taken the rectangular waveguide, and this waveguide is shorted at the two ends along the z direction, and thus it will become, or it will behave as a waveguide cavity resonator rather than a waveguide. Okay. So the field component inside the cavity, it can be calculated using the wave equation by satisfying a particular boundary condition. Okay. So as usual, the way in which we calculated the different modes in the case of a waveguide, which are expressed in a TE mode and TM mode, at that time we have got two suffixes M and N. Now here the cavity resonator circuit are the special case of the waveguide, where the waveguide is truncated along the z direction. Okay, so here we also get the modes of operation. These modes of operation are again TE mode and TM mode, right? But here we will add one more additional suffix, okay? And this additional suffix to these modes are indicative that we are truncated the waveguide in the third direction. Okay, so here the different modes of a cavity resonator are expressed as TE to the suffix MNP and TM to the suffix MNP, where M and N are as usual. These are number of half cycle variation of the field along x-axis. So here it is M, right? So number of half cycle variation along the y-axis, that is here it is denoted by N, and similarly the number of half cycle variation along the propagation direction, that is denoted by P. Okay, so here we will get three suffixes, and in the case of a rectangular waveguide we will get two suffixes, please remember, right? So again the same method over here, we can solve the wave equation and we can rewrite these values. Okay, so for TE mode, EZ component is 0, HZ component is non-zero. Okay, and from that we will calculate HX, HY, EX and EY, which are expressed in terms of three dimension. So the procedure will remain same. The wave number will be calculated as M pi by A and N pi by B as it is usual. And on the similar basis, in the case of TM mode also, we consider HZ to be 0 while EZ is non-zero, and we will end up with the same type of equation. Only the difference between the waveguide and the waveguide cavity resonator is the fact that the resonating frequency is given by here is a little bit different. So if you observe this particular equation, here we need to take into account the third parameter, that is a P part, this particular part. This is the additional part over here. Rest of the resonating frequency is same as that of the cutoff frequency of the rectangular waveguide. Okay, and similarly the same type of formulation can be extended in order to calculate the field equation for circular cavity resonator circuit. Okay, and then similarly for TE mode and for TM mode we will get these equations, TE and TM mode. Okay, and here again x dash MP we used to call it as a root of the Bessel function. Okay, and these root of the Bessel function are same as that of the table we have seen in the case of circular waveguide. Okay, so here I hope that you have understood between the difference between the waveguide cavity resonator and the waveguide. Okay, so when the waveguides are truncated along its direction of propagation by making use of short circuit walls, the waveguide will not remain as a waveguide, but it will get converted into waveguide cavity resonator. Okay. Now we are going to see some of the important types of cavities. Okay. So we used to call them as a re-entrant cavity. Now let us see what is this re-entrant cavities. Re-entrant cavities are utilized in order to construct cavity resonators. Okay, so the microtubes which are designed to transfer the maximum energy from an electron beam to a high quality factor cavity for the amplification and for the oscillation processes. Okay, so microtubes we are going to see in a detail, and a process of extracting the energy from the electron beam is by making use of a velocity modulation process, which we will study in detail when we come across microtubes chapter. Okay, so here what we are doing is we want to achieve maximum energy transfer from certain source to the cavity. Okay, so when the maximum energy is transferred to the cavity will start resonating at a highest power. Okay, so in order to facilitate the maximum power transfer from a particular source, we need to design the cavity in certain special way. Okay, so a typical configuration with which the cavity is constructed, we call it as a re-entrant type of a cavity, and such an example of a cavity is shown in figure number 15. So what we observe over here, a typical re-entrant cavity. So the term re-entrant means the signal or the field is going to re-enter into this cavity again and again. Okay, so the purpose of making such a kind of a structure, this is a cavity actually, right? So this cavity is constructed such that when the field enters into this particular cavity, it will go on circulating between this cavity itself. Okay, so that's why as the field gets circulated within this cavity itself continuously, we used to call that term as a re-entrant cavity. Okay, and such a cavities are required in order to design the resonator circuits. Okay, and other such a kind of commonly used re-entrant cavities are shown in figure 16. So all these are the different types of cavities. We call them as a re-entrant cavities, and these cavities are used in the construction of waveguide cavity resonators. Okay, so always remember that whenever there is a resonator circuit, this resonator circuit, if it is made up of using a waveguide, then there has to be a cavity. Okay, and these cavities are normally called as re-entrant cavities. The term or the meaning re-entrant means the cavities are designed such that when the signal enters into this cavity, it will bounce back and forth inside this particular cavity, and it will set up the resonance operation with which the maximum energy can be extracted from the given source, and it will be imparted to the cavity resonator. Okay, so we go ahead. And anyway, the scattering parameters, their formulation, and the important parameters and properties of the scattering matrix are already discussed. Okay, so again, briefly I will revise you. Properties of the scattering matrix: matched termination, okay, and characteristic impedance, bilateral impedances, electrically symmetrical, electrically anti-symmetrical. Then important property is when the scattering matrix is said to be unitary. Okay, if the matrix is said to be unitary, then it should possess two different properties. We already studied those in detail: zero property and unit property. Okay, and we also studied what do we mean by zero property of the matrix, as well as what do we mean by unitary property of the matrix. Okay, and also we saw the different types of losses which are expressed in terms of scattering parameter. That time we discussed three different distinct types of losses, including your insertion loss, right, attenuation or the transmission loss, and reflection or return loss. Okay, so now we will start with studying the passive waveguide based junction devices. Okay, so first of all, we are going to study the different types of waveguide based junction devices. The primary purpose, now for what purpose the waveguide is being used? The primary purpose of using the waveguide is to transfer high frequency signal from one point to another point. Okay, but shall we use waveguide for this particular operation only? The answer is no. The waveguides are not only used to transfer a microwave signal from one end to another end, but the waveguides can also be used to construct certain specific devices. Almost all these devices are passive devices, and these devices are based on waveguides. Okay, and these devices one by one we are going to study now. Okay, so here, however, there are several secondary applications of the waveguide. Now, by using the pieces of waveguide, resonators can be constructed. And the resonators, we already discussed that resonators are used for the generation of microwave frequency. We can construct windows by using waveguides in order to provide load matching purposes. Okay, so the waveguides can be also be used in this application. Cavity meters we can construct using waveguides in order to measure the frequency of the microwave signal. We can construct attenuator circuit using waveguides, phase shift circuits using waveguide, right? So we can also construct components like twist, turns. Okay, so all these different components we are going to study one by one now. Okay, so first of all, we are going to study the frequency meter or cavity wave meter. Okay, see the cavity wave meter, it is the functional diagram of what do you mean by cavity wave meter is shown over here. Okay, so first of all, let me tell you that this particular device is constructed by using a rectangular waveguide. Okay, and the use of this particular device is to measure the microwave frequency. Okay, so this particular circuit is nothing but it is acting like a tuning circuit, or it is a kind of a resonator circuit. Okay, so the cavity wave meters, these are the secondary frequency standards which are used in measurement of a microwave frequency. These are made by making use of tunable resonator. So please remember, already we discussed what do we mean by resonator. And cavity wave meters or frequency meters are nothing but tunable resonators. There exist two different types of wave meter. The one that belongs to a type called as a transmission type, and the second one which we call as a reaction type wave meter. Okay, so the transmission type wave meter over here, it is connected in cascade between the source, that is a generator, and the load. The maximum energy from the source will reach to the load only when the cavity of the meter is tuned to the resonating frequency, right? In the case of reaction type, that is in the case of second type of wave meter, which is shown over here in figure number B, right? The wave meter is connected to the broader dimension of the waveguide, which runs in between source and load through the vent in the broader wall. The wave meter cavity is placed either exactly near to the broader wall or at a distance of lambda by 2 from the broader wall. This arrangement will facilitate to provide short circuit appearance at the waveguide when the cavity is far from the resonance. Okay, so how this particular device is used to measure the frequency of the incoming microwave signal. Now I will tell you the principle how this particular device operates. Now here the aim of using this particular device is to measure the frequency which is coming from the generator side. Obviously it is a microwave frequency. Okay, so this generator is driving a certain load, and in between generator and load we have connected a frequency meter or a wave meter. Now the purpose of connecting this wave meter is to measure the frequency that the generator is producing. So how to measure that frequency? So we have a rotary arrangement over there, Now, if possible, when we start with our practical session using test bench of microwave in our laboratory, then we will actually perform this particular equation. But for time being, let me tell you how this operates. If we want to measure the frequency generated by this particular generator, what we need to do is we need to simply rotate this meter either in a clockwise direction or in anti-clockwise direction. Now this meter acts as a resonator. Okay, so as on when the tuning frequency of this resonator matches with the incoming frequency of the signal generated by the generator, at that time what will happen is this device will get tuned, and this device will absorb the signal coming from the generator. Okay, so please remember, when the resonating frequency of this wave meter matches with the signal frequency generated by the generator, at that time the signal generated by generator will get absorbed by this wave meter. Okay, so what will happen then? So as the signal is absorbed by this wave meter, the signal will not reach at the load. So at the load, you will get reduction in the signal. Now this reduction in the signal is going to give you dip in the output at the CRO output. So when you place the output device over here in order to visualize the output waveform, in the output waveform on the oscilloscope, you will get dip in the output signal. So dip in the output signal means momentarily you will get decrease in the output, which is shown by the oscilloscope, which is connected to the load. So at that time you need to stop your rotating of this particular meter. Okay, so the moment at which you observe the reduction in the output shown by display device, at that time you need to directly read out the value shown by this frequency meter. Okay, and whatever direct value that the wave meter is showing to us, that is the generated frequency by that particular generator, right? So in other cases, when we rotate this particular meter, the tuning frequency is not matched. So at that time, it will not absorb the generator signal, and the signal will be made available to the load, and at the output display device, we will not get any observed dip in the output signal. Okay, so this is a simple principle how we can measure the generated frequency using this wave type of meters. Okay, so this is one of the device which can be constructed using a waveguide. Now we go to the next type of passive device, which we call it as attenuators. Attenuators are again very important devices, and they are usually a passive devices, and they are used to reduce the power of the signal to the desired level. Okay, the attenuator circuits are very widely used in industry as well as in the laboratory. So how these attenuator circuit look like? See the figure over here. The figure 19 will show us the two different types of attenuators. Okay, one attenuator on the left hand side, it is called as a fixed attenuator, because when you use this attenuator in the circuit, it is going to provide us fixed attenuation with certain fixed amount. Okay, on the other hand, if we want to achieve variable attenuation in the signal, at that time we will make use of this second configuration. Okay, so what is the difference between the first type and second type? In the first type, it will provide a fixed attenuation. For example, if you say if you want to obtain attenuation by 1 dB, 2 dB or 5 dB and so on, so a resistive card which is placed in the path of signal propagation will absorb the signal propagation. So at the other end, the signal, when it comes out, it will get reduced in its magnitude, and thus a fixed amount of attenuation can be made possible using a resistive card attenuators. Okay, so on the other hand, if we want to have variable attenuation, let us say the signal which is going from this particular phase, we want to attenuate by certain variable amount, 1 dB, 2 dB, 3 dB. So the way in which the attenuation is required, what you need to do is you need to press this tapered resistance card. Okay, so there is a spring mechanism with which you can press this tapered resistance card into this non-radiating slot. So what will happen then? this card will get inserted into the direction of propagation of signal. More you press this particular card, it will block the path of the microwave signal propagation, and larger amount of attenuation you are going to get when the signal comes out from the other end. So the attenuation can be provided in a two different ways. The attenuation can be provided with a fixed amount, and if you want to make it variable, make use of this second configuration. So fixed attenuators and variable attenuators are the two main types of attenuator circuit. Okay, and attenuation is required. Now you may ask me a question where we want to attenuate the signal. Okay, so it is very important to attenuate the signal in microwave detector diodes. Okay, so especially when we use diode detector circuit in order to detect the microwave signal. Okay, so please remember, for all the time the same amount of change in the power level is not going to generate same amount of deflection. Okay, so at that time what we need to do is we need to attenuate the signal in a fixed amount. So at that time these types of attenuator devices we are going to make use of. So how to calculate the attenuation? The attenuation is simply calculated using this particular equation 2.248. Okay, so attenuation in decibel is given by this particular equation. It is simply the ratio of 10 log to the base 10, the input power divided by output power. Okay, so input power will be definitely higher in magnitude, and the output power will be a little bit reduced power because of attenuation. Okay, so if you take the ratio and if you take logarithmic scale multiplied by 10, you will get this in terms of a power ratio, and it can be expressed as attenuation provided by that device in decibel scale. Okay, so attenuators are important circuit. They are used to attenuate the microwave signal either in a fixed way or in a variable way, right? Rotary attenuators are also possible, in which you can get a continuous attenuation by the rotation angle. Now the next type of passive waveguide based device is the phase shifters. Okay, so the phase shifters are again very important devices. Okay, so you may ask a question where we use a phase shifter. So phase shifter devices, they find a very wide application in test and measurement system. Okay, but mostly if you recall the phased array antenna system, in which we are going to make use of array of the antennas. So the antennas are multiple, and in that particular case, if we need to adjust the phase of these antennas individually, so at that time we do require to make use of phase shifter circuit. Okay, so phase shifter circuits are primarily used in phased array antennas, right? So phase shifter, which makes use of a ferrite for their construction, are basically called as a non-reciprocal phase shifters. Okay, so how we implement the phase shift in the signal? So particularly if a microwave signal is given to us, how to implement phase shift in that microwave signal? So what is the basic concept? The phase shift in the given signal can be achieved by changing the dimension through which the signal is propagating, or by changing the dielectric property through which the wave is propagating. Okay, so the phase shifting can be accomplished. So beta L, where L is the length of that particular waveguide section. Okay, so beta is a phase shift. Beta multiplied by L, where L is the length of that waveguide section, is equal to 2 pi divided by lambda g, where lambda g we used to call it as a guide wavelength. And this guide wavelength is given with this particular equation. So phase shift can be measured per unit length of the waveguide beta L, which is given by 2 pi divided by lambda g, where lambda g is the guide wavelength, which again depends on the dimension. Please remember, it depends on dimension of the waveguide, that is A over here, and it also depends on dielectric constant. Say from this particular equation 2.250, we observe that the phase of the wave, so the phase part is beta. So how to change the phase of the signal, that is beta of the signal? If you change, you can control the phase shift by varying the amount of dielectric constant, that is epsilon r, which is present over here, right? Or by changing the dimension of the waveguide, that is A, which is over here. Okay, so these are the two parameters with which you can change the phase of the microwave signal which is propagating through the given waveguide of certain dimension. So either you change the dimension of the waveguide or you can change the dielectric constant of the waveguide. It will result change in the phase shift. Okay, and the amount of phase shift, whichever you want, you can vary by either varying epsilon r or by varying the dimension of the waveguide. Phase shifters are shown over here with a different types. Okay, so the phase shifter which is shown in first two diagrams, they make use of a dielectric material. Okay, so certain dielectric material is filled inside a waveguide. Please remember, all these devices, they are constructed using the waveguides only, and that's why these are called as a waveguide based junction devices, right? So in this particular waveguide, we are going to fill it up with certain dielectric material. Okay, and in this dielectric material, we are going to implement a flange like mechanism. Okay, so when we insert this flange inside this non-radiating slot, it will go inside and it will disturb the uniform distribution of the dielectric material, and thus when the signal comes out from this particular end, we will get some change in its phase. Okay, so the other mechanism with which we can implement the phase shift is this particular mechanism, in which we can rotate these rods in this way, either in clockwise direction or in anti-clockwise direction, so that the card inside this waveguide is going to either removed or it gets entered, and thus it will change the dielectric which is present inside this waveguide, and thus it will result in the output phase shift change. The third type of phase shifter, which is shown over here, we call it the squeeze type. So what we need to do is, you need to enter your micro signal from this particular end. The micro signal will get outputted from this particular end with change in its phase. So how the phase is changed? You need to press over this particular part from the both ends. So what will happen? As it is made up of a dielectric material, when you press this dielectric material at the center position, the deformation, so this deformation will reduce the area of dielectric material, and thus the dielectric material will get pressed and it will change the total dielectric constant of this entire waveguide, and which will result in the phase shift when you get the same signal at the output of this device. Okay, so phase shifters are very important and they are usually used in the antenna arrays. Okay, and the last type of phase shifter is a rotary mechanism. Here we have a mechanism to continuously rotate the phase shifter. Okay, so which going to make use of a fixed wave quarter wave plate and a rotatable half wave plate, which are actually are going to change the dielectric constant material of this entire tube. Okay, and if you want to get a fixed amount of phase shift and variable amount of phase shift, that can be accomplished using the different types of phase shifters. Okay, and the next part is microwave bends and twists. Okay, so the next type of devices that we are going to discuss are microwave bends and microwave twists. The bends and twists are shown in figure. See here. So the first two figures are the microwave bends. We call it as bends are nothing but these are the rotary joints, okay, which will facilitate us to rotate the microwave signal from one plane to another plane. So this is a E plane in which the microwave signal can be bent from one plane to another plane in a vertical direction. Similarly, if you want to rotate the microwave signal in the horizontal plane from one plane to another plane, we can make use of a H plane over here. Okay, so what are the bends? Bends and twists. So the twists are shown over here. See here, at this particular side, the cross section is rectangular or it is horizontal cross section, you can twist this waveguide so that this horizontal cross section will get converted into vertical cross section. Okay, so this is called as a gradual twist, and the second is a step twist, in which you can get a twist of 45° at the input. Similarly, when the signal gets at the output, it will get another phase shift of 45°. So the total phase shift you will get a 90°. Okay, so where we use this bends and twist, the bends and twists are made from exclusively the sections of the rectangular waveguide, please remember. And what is the purpose of bends and twists? So here it is mentioned. The basic purpose of using the bends and twists is to either change the direction of propagation of the wave. Okay, so what is the basic feature over here? The basic purpose of using bends and twists is to change the direction of propagation of wave. To change the direction of propagation of wave. So this is a basic feature. Or to change the orientation of the electric field vector of the wave. So normally the bends are used to change the direction of propagation, okay, and the twists are used to change the orientation of electric field vector normally. Okay, so bends and twists are made from the passive microwave component, usually from the section of a rectangular waveguide. If the bending of the waveguide is taking place in the electric plane, we call it as a E-plane bend. On the other hand, if we bend the microwave signal into its H-plane arm, we call it as a H-plane bend. The two types of bends are shown over here in the following figure. Okay, and the bends are very important, and the reflection due to one particular bend is a function of its particular radius. Okay, and the second important aspect is the double meter bend is used, which gives low values of VSWR and O. Now, similarly, the twists are also made up of from the rectangular waveguides, and these are useful to change the orientation of electric field vector of the microwave signal. Okay, so the twists are shown over here: gradual twist and step twist. So the first type over here is a gradual twist, and second twist is a abrupt twist, that is a 45° twist. Okay, so what the gradual twist will do, it will orient the microwave signal from the horizontally polarized direction to vertical polarized direction. Okay, so normally the twists are especially used when we want to change the orientation of the microwave signal. Okay, and finally, the different types of a termination we are going to discuss. So normally the terminations are of three types: matched termination, open circuit termination, and short circuit termination. Okay, so waveguide terminations are also called as end entities in the waveguide system. Okay, so the terminations are required to be placed at the end of that particular circuit. What they represent? They represent end part or the end system in the waveguide based microwave system. Three types of waveguide terminations. First is a match termination, right? Second is a open circuit termination, and third is a short circuit termination. Okay, so wherever we require to keep open circuit, short circuit, and match termination, these devices we can make use of in the circuit, and they can be placed at the end of the particular circuit. Okay, so waveguides are often requires match termination. The match termination makes use of resistive or absorptive material, which could be able to absorb the field which is incident upon it. As the field gets absorbed, there will not be any reflection from the match termination, and hence standing wave remains 1. Okay, so match terminations are very much useful in order to absorb all the reflection, right? So for the given waveguide, the match termination is achieved. So how to construct the match termination? It is achieved by filling the end of the waveguide with a graphite and sand mixture. Okay, so here we can achieve or we can construct the match termination by filling the rectangular waveguide at the end side by using a material like graphite and sand. Okay, and on the other hand, how to construct the open circuit condition? It is unlike two-wire transmission line, it is not possible us to provide open circuit in the waveguide. by just merely leaving the terminating end as an open circuit. Okay, so what it will cause is, if we keep the waveguide end open circuited in order to achieve the open circuit, it will cause irradiation from the open end. Therefore, in order to provide open circuit condition in the case of waveguide, the insertion of quarter wave transformer section we normally provide, right? So waveguide terminations are basically three types: match termination, open circuit termination, and short circuit termination. And these terminations are especially used at the end system of the microwave system. Okay, so here all the basic waveguide based passive devices we have discussed, and later on there are still more junction based devices are left. These junction based devices, again, they are fabricated using pieces of rectangular waveguide section, and in our next lecture we will see the details of all these passive microwave junction based devices. So today we discussed the investigation of the field components of rectangular and circular waveguides, whose derivations we already done in our previous lecture. We have got the greater details into the inside of mold field patterns, and there afterwards we saw the resonator circuit, how they are constructed and why they are called as a special case of a waveguide. And there afterwards we revised some of the concept of scattering parameter characteristic, and then afterwards we started with the passive waveguide based devices, starting with wave meters, attenuators, then phase shifters we have seen, and then finally bends and twist and termination. Okay, so in our next lecture we are going to start going into the details of other type of passive wave junction based microwave devices. So over here I stop, and let us meet next time again. Thank you very much.